on that side of the monsoon precipitation, you might be able to take advantage. And so the first thing you might notice about roots, particularly in perennials, is the concept of a dimorphic root. Dimorphic, two morphologies. Shallow roots and deep roots. And in some plants, the shallow roots take up water only. No, I'm sorry. In some roots, in some plants, the shallow roots take up nutrients only. And in some plants, they take up water and nutrients. So there is no hard and fast rule that I can give you. If you want to be a global ecosystem modeler and say plants only behave in one way, you're forgetting about natural selection and evolution. Okay? You do that at your own peril. We find that you can do experiments of adding N15 fertilizer and 18O labeled water and see if plants take up one versus the other. And you get very interesting results that are suggestive of very distinct patterns that not all species respond the same. So without giving you countless examples, I just want to lay out the principle. Don't assume if a plant is taking up nutrients, that it's taking up water. Don't assume if a plant's taking up water, it's taking up nutrients. Don't assume that the same root system is going to be active the entire time. Yes?
Are nutrients dissolved in water?
They are dissolved in water, but in order to take that nutrient up out of the water, you need an ion channel that's active. So it's entirely possible that you can have a root system which has water in it, and it takes up the nutrient through the ion channel, but the aquaporins are not active. So if you think about it as two different gates, both gates don't have to be open at the same time, it's not the same gate. One gate is associated with a polar but non-charged molecule, the other is associated with a charged ion. Now, yes?
You talked before about the traceability, that as traceability. So if you're talking about this plant with different level of residues, how does that can really
So how can we use isotopes to study root distributions? Cool, easy. In this way that we suggested, if we know the isotopic profile, which you can get quite easily, then you have the potential of asking which roots are active and which roots are active over time. So how am I going to do this without digging up the plant? I'm going to be lazy. I'm going to let the plant take the water out of the soil, and once it's in the stem, I'm going to measure the isotopic composition of the stem. And I'm going to measure the isotopic composition of water in the stem over time. And using an experiment like that, I can determine whether the plant is using water from the surface or from depth, or if it's changing. And to go back to this graphic here, I think it's, yes, to go to this graphic here, where I have plants that are using water at different depths, that's after the rain event. What you need to ask me is, hey Jim, what happened after the soil surface dried out? And you know what happened? The annuals stayed at the same value. They didn't have deep roots. There was very little water. All of the herbaceous plants and all of the woody plants shown there, they switched to that water source. They said, I've got two sets of roots. Let's turn off the roots. Let's not take in water from the surface. There's not much left. Let's go back to the reliable source down deep. So that's, in fact, how we end up using it, and I'll give you some examples. So this shows that there's water source partitioning. This shows that you can have multiple species in the same area, and you can't, without looking at water sources, determine who is or who is not competing. So isotopes become a very useful way for you to begin to make that study. Now, 1 second, don't take your question. Why do I mention this in these patterns here? Because this graphic describes the changes in water content that you see in our part of the world in most arid and semi-arid regions over time. We have pulses of moisture that come down to the surface. And as those pulses come down, we saturate the upper layer, and then it dries out. Saturates it, dries out. So if you look here at the black and white circles, which are 0 to 5 centimeters and 5 to 15 centimeters, you see that those soils are getting wet over time, they're growing out. They're getting wet, they're growing out. And if you now look at the isotopic or the soil water content down deep, which is more than a half a meter, then you find it stays constant. I got a reliable source. I've got a dynamic source. For reasons that I don't think I can go into right now, because I don't know the answers for sure, why do the plants switch? You know, you might think about it in terms of your own behavior. If you had something reliable and something that was there for a bit, might you take advantage of it? I don't know. Okay, there was a question here.
Yeah.
Yes,
So,
Maria. Right.
Maria, how correct is to assume that the sampling moment of the soil and the xylem, that the xylem water corresponds to the soil in the moment of the sampling due to, for example, capacitance?
Yeah. So the question is, if I do a grab bag sample one time, how sure can I be that what's in the plants reflects what's in the soil? If it just hasn't rained in the last 48 to 72 hours, it can be very reliable. It's very reliable. The water within the xylem system will turn over if a plant's transpiring in about 24 to 48 hours. So if we take these plants that have been inactive and we add rain in the desert, it takes about 72 hours for us to see it. That 72 hours isn't because it takes that long to go through the root system. The root systems were inactive, they're now being activated. If we have active roots, and we now add an isotopic label, how long does it take? 12 hours, 6 hours. It's very fast. So remember, if water uptake is related to aquaporins, it's not totally passive. It takes time to turn on these proteins. And that, to me, is the fundamental insight which has taken place in the last 5 years. If you look at most textbooks today, they will say that the uptake of water is a totally passive process. They are so incorrect. I don't want to say that's fake news, but what I will say is that we were not taking into consideration a body of literature that we chose to ignore, and that is that you can either through poison or through cold temperatures reduce water uptake. And if it's a physical process, poisons and temperature shouldn't have any effect on water uptake. Okay, so let's give you an application. One of the best plants we have in Utah, Utah juniper. If we look at the Utah juniper, and we sample before a rain event, and we sample after a rain event, we see something pretty cool. We're going to, Jill Gregg went to 4 different sites, Salt Lake City. She sampled before the rain event and after the rain event. The before the after rain event should be the isotopic composition of winter water, because this was in the summer, so -100. And after the rain event might have been -50 or -60. And when she looked to see what happened in Salt Lake City, those plants didn't even know it rained. They didn't take advantage of that water. So the isotopic composition in the beginning, before the rain and after the rain, was the same. Okay, now let's go on all the way down here to the Grand Canyon. And when she did it at the Grand Canyon, it was -80 before the rain event, and after the rain event, -70. The plants switched from a deeper soil moisture to take advantage of that surface moisture. So wait a second, Sergio. I got the same species in the Grand Canyon as I have in Salt Lake City. And in one place, it's taking up water. Another place it's not. So what she did is she said, let's go here to the Navajo Nation. Let's go here to Zion National Park. And what you see in this graphic here is that when you cross the long-term monsoon boundary, you get into the boundary, within the monsoon rain region, plants take it up. We have ecotypic adaptation. So we have the same species, but we have genetically distinct populations, some of which have active summer roots, and some of which don't. Tell me how cool is that? Now this goes to explain a number of really important observations that people have made in restoration ecology. Turns out, my job, Sergio's hired me. My job is to restore junipers. And so what do? I have a plantation in northern Utah, and I'm restoring plants in the Grand Canyon. And my plants don't take off, they don't die, they die. I have the wrong genotypes. I have the wrong ecotypic population. And so it's that recognition which is really quite important, and it's just not true for juniper, it's true for quite a few species. Yes?
How do you know that it's genotype versus phenotype?
Transplants.
Okay.
Transplants. So I didn't want to tell you that part.
You did that too.
We've done the transplants. Now what you notice, which is relevant for ecology, is the following. That some species, and this is a macro observation, some species have distributions that cross the monsoon boundary, such as the Juniperus osteosperma that I showed you. Other species are really cool. Juniperus monosperma only grows in monsoon climates. It doesn't make it across the monsoon boundary, whereas Juniperus osteosperma does. So we have some species that are only found north of the monsoon boundary, some of them are only found south of the boundary, and some of them that cross. You see that as well for Pinus edulis, which is the pinyon pine. Anyone here like pinyon nuts? Okay. I could help you by sending you out to collect them in a site that has Pinus edulis, and you'll find them. Or I could send you out and say, hey, they're just out here in the West Desert, go look. And you'll never find any because they aren't on the Pinus monophore. Now, we have very distinct distributions, and they stop right at the monsoon boundary. But here's the really cool thing. These trees live for a couple hundred years. And if you go to northern Utah, you can find some places where we have hybrids between the two species. How in the heck do we get hybrids? Suggestions? Monsoon boundary moved. There is good evidence to suggest that the monsoon boundary moved during the 1200, 1300 year period. Oh, that's about the time that the Anasazi decided that they would vacate, their lease was up. They decided to leave southern Utah and New Mexico. It's also at the same time that Native Americans on the shore of the Great Salt Lake decided that they would stop eating corn. No one stops eating corn. But if you lose the monsoon rains, then you don't have an irrigation system. Okay. So the evidence suggests that this boundary is dynamic and that it's changed over the last couple of years. One other example. So I'll tell you, so that's a summer rain example. Now I'm going to tell you about a summer fog example. This is the work of Todd Dawson. The change in moisture can come by a change in rain systems or in water sources as in the form of fog. And what Todd and his colleagues have been studying is how dependent are species on fog as a water source. So we have these wonderful fog systems. And the other question you might ask is, if it turns out a species is dependent on the fog, can they all take up fog water on their own? Or do they need the redwoods to trap the fog for them? So I can tell you the very short answer. Most species do not take up fog on their own. They depend on the drip, drip, drip coming off the redwood tree. So this is what we might call a keystone species. It is critical to the functioning of the system. So what happens? It's the same system that we have that brings the summer rain to southern Utah and Arizona. There's a movement northward of the Pacific High. It's called the blocking high. And as it moves north, those northern storms can't come down. It allows summer moisture to come up into the eastern Pacific for the southern part of the state, but it enhances the rate of upwelling. And as it enhances the rate of upwelling, those cold waters come up and they create fog. And that fog then becomes a water source. So here's a series of the players. But here's what I want you to see. Let's just spend a few minutes looking at the graphic. So that blue line at the top is the hydrogen isotope ratio of fog for the years 1992, 3, and 4. Same pattern is there all the time. Okay? The lines that are below it are the isotopic composition of water in the stem, therefore the isotopic composition of water that all these plants are using. And notice that when we have fog periods, that the isotopic composition of the source water goes up, begins to approach that of the fog, implying that it might be the source. During the winter months here, where the isotopic composition of precipitation is lower, it looks like the isotopic composition of the plants goes down. So there's the suggestion in these data that the isotopic composition of the water used by these plants varies as they have winter precipitation available as a source with no fog, or summer precipitation absent but fog present. And what Todd did is begin to use what we call a mixing model. And in a mixing model we say, here's the isotopic composition of fog, here's the isotopic composition of precipitation, and now let's calculate what percentage is in one species versus another. And that's shown here from the bottom. And what you see is that it tends to vary over the course of the year, but the amount of fog which is used is less than 10% or as high as 100%. Then on average, the Sequoia sempervirens, which is the redwood, is getting about 40% of its water from fog. You can do the eradication experiment, get rid of the redwood tree. I don't propose doing that experiment, but loggers have done it. And then what you see is that the other species do not persist. They may not use the 100% of the fog necessarily, but they will not persist without some fog from these trees. And they don't have the capacity, it seems, to take the fog out of the air. Now, taking the fog out of the air is a very passive process. You need something to block the moisture coming in, have it precipitate out. So that's a big redwood tree. It's a beautiful example, as is the other one, of showing that there's variation in the water source of plants and that you can capitalize on that as a tool. Questions? Is it possible for plants to capture water in an arid environment? Can you give me an example?
Well, some trees have tanks where they try and capture water here. I mean, you can have some forms of cyclones too.
Some forms of cyclones? Okay. I'll tell you the answer is yes. It's not Maria. Laura. Laura, the answer is yes. And the best example is the Loma. The Loma in Peru. And if you look at tobacco, which is an annual plant there, that tobacco germinates in the spring, and it shoots up, and it has roots only in the surface, like its roots are only in the top 5 centimeters. But it's got these leaves, they're huge, and they're flat. And when that fog comes in, they just trap it. And if you look to see how people reestablish trees in that part of the world, they don't come out with their irrigation pipes. No, they get a piece of sail, and they make it triangular in shape with one point down at the root. And they simply trap that moisture as it comes by. So it is true that in the Loma, probably the area I've seen it the most, that there are a lot of plants that rely on fog. In Baja California, I think they do as well.
Yeah,
Yes?
there are also some examples in Amazonia, like the driest forest works from Rafael Oliveira, where he finds some water foliar fog uptake, and he also sees like hydraulic redistribution of that water with isotopes.
So let me try to explain that. So there are many situations, some subtropical, some arid land examples, where plants have the capacity to take water out of the air at 100%. It's a facultative condensation. They then have, in some cases, the potential to redistribute that water from a shallow depth to a deeper depth. Maybe internally, maybe externally. So there are lots of ways that plants can play this game. An important thing to remember is, A, the laws of physics will always work. Water goes from a region of high water potential to low water potential. High, let's say a -2 to a -6. So Lujan gradients of decreasing Gibbs free energy. That's the first thing. And the second thing is that if water is going to leak out of a plant, you need active aquaporins.